In this video, we are going to learn about computing surface integrals. The particular application I'm looking at is Stokes' theorem and divergence theorem in electromagnetics. But this video is just about the general mechanics of taking the surface integral. We want to take the integral of the vector field A, passing through the surface S, to learn about the flow or flux of that vector field. The first step is to choose a coordinate system. If the surface is closed, we want to break it into pieces that are easy to integrate over. Then we will choose the correct differential surface for each piece. We then take the dot product of the vector field and the differential surface, evaluate the integral for each piece, and finally, sum the results of all the integrals. So how do we choose the correct differential surface? Well, it turns out that if we are calculating the outward flux through a surface, we're going to point the normal vector for each piece in the outward direction. Then, the differential surface needs to point the same direction as the normal vector. An easy way to find the correct ds is that we want to integrate over whatever differentials will cover our surface. In Cartesian coordinates, let's suppose I have a rectangle on the xy plane, which has z as the normal vector. Then I would want to integrate over x and y, so I'll choose ds that has dx dy. The direction then is determined by aligning with the normal vector pointing outward. In this case, it would either be plus or minus z hat. Let's look at an example. In this example, I have a cylinder, so the coordinate system that makes the most sense is cylindrical. The cylinder has three distinct parts: a top, a bottom, and a shell. At the top, the height z is a constant at 2, but the radius and angle can change over that surface. The same is true for the bottom, but the height is constant at 0. On the shell, the radius is now constant at 2, and the height and angle can both change over the surface. We can now choose the differential surfaces for each piece. The normal vector for the top points in the plus z hat direction. The normal vector for the bottom points in the negative z hat direction, and the normal vector for the shell points in the positive r hat direction. We will combine the steps of taking a dot ds and the integral to save some time in writing. If you need a refresher on taking the dot product, see episode 8 of my how-to series. Starting with the top piece, we realized from taking the dot product that the only part I need to integrate is the z hat component of the vector field multiplied by r dr d phi. Taking this integral, I'll get negative 48 pi. For the bottom, we're going to take the same integral, but the differential surface points in the negative z hat direction. When we plug in z equal to 0, we notice that this whole integral becomes 0. For the shell, we only need to integrate over the r hat component of the vector field multiplied by r d phi dz. This integral gives me 160 pi times e to the negative 2. Summing the results gives me negative 82.8. So, we have learned that by following this procedure, we can compute surface integrals. The only difference between the example I gave you and different geometries is that we may use a different coordinate system. Thanks for watching. Look for more videos coming soon.